Hello, everybody, and welcome to our latest Hubble Hangout. My name is Tony Darnell. I'm the social media manager for the Space Telescope Science Institute, and we haven't done one of these in a while. This is our first Hubble Hangout, I think, since November. Is that right, Scott? Something like that?
I think it's been November. It's been
a
while. You and I have been up to trouble.
Yeah, we've been doing other things, but I think it's our first one since then. We kind of took December off a little bit. But this one is the first one of 2014, and it's a really exciting one for me because it's all about citizen science. So today we're going to be showing you a brand new initiative that has been launched today that allows you to help astronomers do science using the Zooniverse, another project in the Zooniverse universe, I guess. The Zooniverse universe. So with me today is a whole host of people that were involved in the project, but my co-host, as always, is with me, Scott Lewis from KnowTheCosmos.com, also known as the Bald Astronomer. Hi, Scott.
How's it going, Tony?
You're going to be a guinea pig today.
No, I feel like guinea medium.
Guinea.
Yeah.
Because we're going to have you step through.
I have not gone through this software, so I'm going to test out and see how this citizen science project works, and I think it's really cool being able to test, find the age of stars in this galaxy.
Yeah, it's going to be. Well, that's one of the great things about all of the Zooniverse things is how it gets people involved, and Laura, I'm sure, is going to help us talk a little bit more about that as well. But before I get going and introducing people, I want to let you guys know how you can interact with us. Always use the Hubble Hangout hashtag if you want to. The humble Hubble Hangout hashtag if you want to tweet.
The alliteration is strong in this one.
I know. I just can't help myself. I always have to do that. And so that's how you can get our attention on Twitter. I've got that up on my tweet deck. We're also taking comments via the Q&A app on the event on Google+. If you ask a question on that, you push the button and ask a question. We'll see it, and we'll try to get to it as soon as we possibly can. There's also the YouTube comments. I'm looking at those as well. And
be nice, YouTube.
Yes. Yeah. Well, actually, they kind of have to be nicer now because YouTube is making them. They're making them more accountable for their comments now, which is kind of nice. So that's how you can get a hold of us. We will have a segment toward the end, or maybe even throughout, if it's something that's relevant to what we're talking about. I'll interrupt and ask your question during the Hangout as well. So let's get started. And let me start by introducing Dr. Brad Whitmore. He's an astronomer at the Space Telescope Science Institute, and I think you are the PI for this. Is that correct, or am I?
Yep, pretty much.
Okay. So why don't you describe for us what this is we're doing today?
Okay. Let's see. So I should grab and share. Screen.
Hang on just a second before I do that. I apologize. I want to get through. I want to introduce everybody first. And with me also is Dr. Bill Blair. He's an astronomer at the Johns Hopkins University and at the Institute. Hi, Bill. You're going to be here to help explain us some of the science behind what people are trying to do. And,
looking forward to it.
What's that?
Looking forward to it.
Yeah, great. Thank you and welcome. Also is Dr. Carol Christian. She is the HST outreach scientist and a geek goddess. You want to explain that?
For one brief minute, yes, we had a press release. For 1 week, I'm a geek goddess with my collaborators. We are creating a completely different project. We're creating 3D printouts of Hubble images, and in particular, putting textures on them for the blind, and we'll do a hangout on that sometime in the future.
Yes,
we will.
Great.
I will make you, Carol.
Okay.
I love it. They're amazing.
We'd love to.
And also is Laura White. She's from the Zooniverse team. Is it Doctor or just Laura?
It is actually, yes, Doctor.
Okay, good. Dr. Laura White. Welcome. She's going to describe to us a little bit about the collaboration with M83, the M83 project, and also if you've never heard of Zooniverse before, which I would find it very amazing if you did not, then she'll also get us familiar with that as well. So welcome, Laura. Thank you.
No problem.
And finally, we have Tom Donaldson. He's the what are you at the Institute? You're an astronomer too, right? You were in the data archive and MAST and things like that, right?
No, I'm a computer scientist.
Okay.
Mostly currently working for the MAST archive.
Okay. So you were instrumental in getting some of the behind-the-scenes stuff written and getting the nuts and bolts going, right?
Yeah, I worked a lot on the user interface and figuring out how to talk to the Zooniverse world, which was a lot of fun to learn about.
Oh, good. That's great. We're going to find out what you went through to do that. So let me get back to, and I've already introduced Scott. He's got to just cause mayhem whenever possible. So,
I'm breathing, right?
give us an overview of the project, what it is you're doing here.
Okay, let me jump to screen share, grab this one here, hit the little button, and I'm live, right?
You are live.
Yeah.
We're
All
on
right.
Get Your PowerPoint.
All right. So I'm stealing a couple view graphs I used at the American Astronomical Society meeting last week. And so the name of our project is Stardate M83. It's a citizen science project where the goal is to age date star clusters. And the centerpiece is this wonderful new Hubble Heritage image right here. Maybe you've already seen that. If not, you should Google that and go find a zoomable image. It's really fantastic. This is the first time that we've actually had a Hubble Heritage image with a citizen science program attached to it. It's a joint project with Zooniverse and the Institute. And before I forget, this has been a real experience and a tremendous team to work with. So I want to kind of thank everyone involved, people online especially. Okay, so what is the science behind it? In a nutshell, the idea is that we think we can measure the ages of star clusters by simply looking at them. I actually wrote a paper here in 2011 where we gave that a try. So I won't describe how astronomers generally measure ages in detail, but they use the colors. And the thing is here, I thought by just looking at them, I could also estimate the ages. So I put together this little paper, and these are essentially what the citizen scientists are going to do. You can see for the very young ones, they have this pink cloud around them. That's from hydrogen gas. And as soon as you see that, you know it's very young. And then if you can see the individual stars here, that's young or intermediate. And then they get kind of fuzzy looking. And then most ancient ones have this kind of yellowish picture around them. Now, a question I get asked a lot here, why are we doing this with citizen science? Why don't I just have the computer do the whole thing? And the bottom line for this project especially is it's that H alpha. It's the hydrogen emission, the pink clouds. As you can see, they can come in any shape and size. And so if I just plop down an aperture and measure the colors, in many cases I've completely missed the hydrogen. And so it's much easier for a human to look at that and say, oh yeah, okay, well it's kind of centered around it. I think it's blowing this bubble of hydrogen. This must be a young cluster. So
let's go back to that just real quick, Brad. That aperture, that yellow circle there, yep. That is what would be used by an automated program, right?
Exactly.
If you tried to do this automatically without a person, an automated program would easily miss any hydrogen because of where that circle is. And even if you move it around quite a bit, you're still going to miss it.
And you could say, well, let's just pick a gigantic aperture and make sure we get it, and then we're going to get 2 or 3 or 4 other clusters and all kinds of other junk. So you really have to kind of stay in close to the center.
You run into the limitation of the software when you do that. Okay.
Right. Okay.
So can I get you to go back one slide for just a moment?
Sure.
There's something I want to ask you about. So go back one more. The third one, number 3.
There we go.
Right there. So here is where you're saying that there are 3 different diagnostics here, but the second one, if you can see individual stars, then they're intermediate age. Doesn't that just mean you've got a really good telescope and you can resolve the stars? Well,
at the distance, the bottom line here is that the brightest stars, since they are so bright, they're using their energy really fast, and they just don't last. So at 10 to 20 or to 30 million years, and they'll have they've faded or blown up, and you can't see them anymore. Now, you're right that, if we had the world's greatest telescope from space, you'd actually be able to see the individual stars for the fuzzy ones. But since these are all the same distance, that difference allows you to kind of tell which are the intermediate age ones, just from whether you can see the bright ones or not.
Okay, so, but even in the young, I can see individual stars, so I would get confused. I can tell you now if I'm classifying.
But the first question, the main one is, does it have hydrogen around it? I mean, It's exactly right. You can still see the individual clouds, but here you can't, and so it's more than about 10 million years old.
Okay, all right, I see.
So this is kind of 1 to 3, giving numbers, 3 to 10 million, 10 to 50 million, more than 50 million, more than 500 million years old.
Okay,
and that's kind of all in the paper.
So we have this really high-definition image of a galaxy, and we've already seen why an automated program is going to have trouble finding these hydrogen gas clouds. But you're saying that it is possible, based on the paper you wrote in 2011, that you can look at what a star cluster looks like and be able to estimate its age based on certain characteristics. And here they are. Right. This is outlined hopefully on the webpage. We'll get to that in just a bit. Okay, thank you.
And
I just wanted to clarify a few topics. You can go ahead.
And the improvement in our own science is we're going to do both and use the best of both and combine them.
Okay.
So let me
great.
go ahead and let's see. How do I share the next? Is that up, or do I have to hit share again on that?
What do you want to share next? The
web page itself.
Yeah, you'll have to click the screen share button again.
Do it again.
And
Okay, here we go.
And select it. Okay, while he's doing that, should I?
Here we go.
Okay, you got it up?
Yep.
Oh, that was fast. Okay, go ahead.
Okay, so I'm going to run.
Here it is. The gateway.
I'm going to run through the tutorial.
Yes.
When you first go to the page, this is what you'll see. I'm going to skip the about the science and stuff. Bill may come back for that a little bit, and do what any good American would do, or anyone in the world. Just hit start here. Don't read the instructions. Just kind of jump right into it.
So first off, the URL is projectstardate.org. That's where you're going to go to get started. And Laura, let me ask you. Well, a lot of people who are familiar with Zooniverse already have logged into other aspects. If they've done this before, will they already be able to use their account?
Absolutely. A normal Zooniverse account will work on this project as well.
Awesome.
So any project that they've tried should the same account will work.
Great, thank you. Okay, go ahead, Brad.
Okay, so we kind of run through this little tutorial. I'll let you read most of it when you do it yourself. But the bottom line is we kind of tell them, first of all, most of these are stars, but in the center in this particular case is a cluster, a very dense cluster of stars with several hundred or even thousands of stars. And then we're going to ask the same questions that I just mentioned. Is there a pinkish cloud roughly centered around it? And in this case, there's not. And so we're going to hit no cloud. You can get information over here and look at some examples, etc. So no cloud here. Here's this question about whether I see individual stars or is it fuzzy looking. I'll give you a little hint here. You could zoom here. You can see it looks pretty fuzzy. So let's hit fuzzy. Okay, here's the color, and this can be a pretty subtle difference, but we just ask you to do your best. So you see the ones at the bottom are a little bluish, ones at the top a little yellowish. This is kind of in between. So there we are. Those are the three questions already. Now, as we did that, hopefully you were maybe noticing over here that the ages were being trimmed down. Each time I answered a question, it changed over here. So we've established that this is an old cluster. Here's a zoom. Okay, so we've age dated it. The next thing is let's go ahead and measure the size, and we give you a little practice thing here. As I move that, you can see the shapes changes. There we are, about like that, say. I can move it down a little bit. I can rotate it if it wasn't kind of spherical. Looks pretty good. We get, again, some instructions over here.
Okay.
Also, I might point out this help here for kind of more detailed instructions. Here's some more examples, some things not to do and some things to do.
Okay.
So we got a little more help there. Okay. Now, in some cases, as we mentioned, we have these pink clouds around them, and we'd have you measure that also. But we'll just kind of march on. And the third step, the last step here, is to just do a little bit of exploring. And here's a bunch of things to look for. Background galaxies, single stars with pink ring, supernova remnants right down the line. I'll just flip through. Oh, dust clouds, Bill's favorite. Okay, and some artifacts that you might kind of watch for. So a whole bunch of things to watch for. Let's go ahead.
In the tutorial because you're going really fast. So this
yeah.
is all,
I was assuming that they could kind of go back and kind of play with it themselves too. But yeah, any
okay, Brad, because I'm about to do this live on air, and I don't want to make a complete fool out of myself.
Okay, well, you have to be paying more attention then. So, okay. So if I look around here, there's mainly just individual stars, but I see some little pink clouds over here, and the central object here doesn't look kind of big and fuzzy. It looks like an individual star, like these other stars, and so that to me is, that's something worth clicking. Okay, we're gonna mark that, and what does that look like? It looks like a single star with a pink ring. Okay, so I've explored this.
So what is that? What does that signify? That single star with a pink ring? That's just a star with a gas cloud around it?
Yeah, it's very similar to these other clusters, but the clusters have hundreds of stars or even thousands, and so they can ionize or make the hydrogen cloud a really big one. A single star can only make kind of a little bit of a ring. Okay.
So you're not just dealing with star clusters in this interface. Then we're also asking people to find other things and look at other objects.
Right. It's optional. We say if you like, you can explore, etc. We'll put together different samples of different kind of objects, and we'll go back and study those, for example.
Okay.
Okay. So that one's finished that. Here we'll give an example of what they gave and finish up. Now, before I kind of go to next cluster, I want to point out one nice little feature here where it says, where am I? So where am I in the galaxy? I've got this little thumbnail, but now I see, oh, I've been working on a little cluster way down here.
Wow,
right.
Oh, that's really cool.
Yeah. So I wanted to make sure people saw that. Okay, and now I'm all set. And so I just hit next cluster, and away I go. And at this point, unless we have a couple questions we want to address, we'll put Scott to work.
Oh, great! No pressure. Just
Okay, so so that to me looks like just a star, right? Can I zoom into that? Zoom into that.
There's the zoom, and so here are individual stars here. That's probably another cluster. So you can see it's a little more nebulous. I can actually see a couple little.
Whoa! You just said the other one is probably another cluster. Where is that?
Oh, down here maybe.
That looks just like the thing in the middle.
Yeah, exactly. This is a cluster.
Oh, that is a cluster.
And that's
Yes.
And all these things here are individual stars.
Okay, so based on the thing on the left, that looks like it's probably old. Would you agree?
Oh, you're trying to jump ahead of the game, huh? Yeah.
Well,
Yep.
I'm just trying to make sure I understand it.
Yep.
Okay.
Right. And just
Good work, Tony.
yeah.
and maybe I'll
You
point
should
out
do
right
like
now that
YouTube videos about this stuff, Tony.
once you're kind of trained, you could hit the fast track here if you don't want to answer the questions all the time, and then you can look at a few more. So here are the intermediate age ones. Here is the old ones, and Tony thinks it's old, like these, and he's right.
Yep.
Okay. Awesome. Okay.
So there we go.
They had to have fast track for me because I can't stand to read all the questions. I just want to do, bam, bam, bam.
I don't
Classify the
believe you,
question.
Carol. You
You're
seem like the
a
most
goddess.
patient person in the world.
You're a geek goddess with ADD. We got to keep your attention, you know.
Absolutely.
Okay, so Bill, let me ask you a couple questions here. Brad's shown us the interface, and he's given us a brief introduction into how to use it. So, you know, we go over here to projectstardate.org, and we're going to be given a bunch of classifications. We're going to be even identifying some stars and some other things that are in this galaxy. Why don't you tell us a little bit about the science behind what you're trying to do? What are you trying to learn?
Okay, I'm trying to bring the site up here so I can point to a couple things as well.
Okay, we see it. It's up.
Okay, good. So here's our front page again where Brad started from. And if you want to learn more about the science, there's this About tag up here, pull-down menu. About the science comes up. Can you see that okay?
Yep, we're with you.
Yep, good. All right, so About the science, and you can kind of go through and learn a little bit more about the background science. Now, in reality, you don't have to know anything about the science to do the exercise. But we hope that people are intrigued enough by it to want to understand a little bit more. So there's a brief description of it up here. And basically what we're talking about here is the life cycle of stars. Stars, almost all the stars in a galaxy start out life in one of these clusters, we think. And over time, of course, the more massive stars evolve and start to go away with supernovae or whatever, and leaving the lower mass smaller stars behind, and that's the evolution that you're seeing as you date the clusters, and different clusters or different ages, different amounts of stellar evolution have happened. Interestingly enough, not part of this exercise, one of the parts that I'm interested in the project is a little beyond where you turn off at the old clusters, and that is the supernova remnants, the things that are left over after supernova explosions is what I'm most interested in. So that's the end stage of the stellar life cycle, if you will. Sometimes we call the remnants, the things that are left over after the supernova, we call them the ghosts of dead stars. So the project overall is really looking at everything from the beginning of the process through the evolution of the star clusters, through the dispersing of those star clusters out into the general field of stars in the galaxy, and then through the supernova phenomenon, dispersing that material back out into the galaxy. And when you see a picture like this of M83 with all the star formation going on, with all the clusters, there's about 300 known ghosts of dead stars in this system. You see all the brown dust lanes in this galaxy. A lot of that is material that was in stars at one point, that was processed into heavier elements, that was thrown back out into space through the supernova process, and then the process then formed interstellar dust bunnies all over this giant spiral galaxy that we call M83. You see that
Interstellar dust bunnies. Nice. I like that.
I didn't think you'd let that go by, Tony.
Yeah.
Jeez.
So whenever my house gets too dusty, I'm like, it's the universe's fault. The interstellar dust bunnies.
I like that analogy a lot, because even though this stuff looks very dark and like they're huge clouds. I mean, many light years, hundreds of light years across, but the density is very, very low. So that's why I like the dust bunny analogy. It's just like little fluffs of stuff out there in interstellar space. Also, under the About button is about the project, and you can learn a little bit more of the background that it's taken to get us to this point, the observations that we took, the background that Brad was describing, how we get ages out of this information, and then you can see about the team here if you'd like to read little bios of the people there. And then also, if you want to get a quick link to get to the Hubble Heritage site, is right here as well. You can see that we are the monthly image this month, just put up last Thursday. Clicking on that brings up the bigger one, and from the tabs at the top here, you can get to a lot of additional information, fast facts about the galaxy, what the filters were that actually went into it, that sort of thing.
Okay, keep this up. Go to the top here. I want to learn more about this image here. So you started out with a where'd you go? No.
I'm sorry, I went to the caption. Sorry. You want fast facts again?
Yeah, go back. Yeah. So is there? Tell me. So you have Hubble Heritage is this project that takes some of the most beautiful pictures of the Hubble Space Telescope has ever taken. They do it usually for aesthetic reasons, but sometimes, as in the case here, we're able to do a lot of good science with it. So this image is a very high resolution image, correct?
That is correct.
What is the resolution? Does it say that on this web page here? About the data. How big is the image we're looking at? Because it's zoomable.
Yeah, there is a link to the zoomable version over on the news site. Let me see if I can find that.
So basically, this entire project is built around this image, and so we are mining the not necessarily the numbers from it, but the shapes that can be gleaned from this image. So.
Bill, I've already put a link to the zoomable image in the event page. So any of you watching on Google Plus that want to take a look at the zoomable image of this, just check the Google Plus event, and it's in there right underneath the actual image itself that I've embedded.
That's great.
So I pop back to the overall image again. Let me just describe that. Basically, what you're seeing here is about 6 different fields of the Hubble Wide Field Camera 3 that have been stitched together. So there are 6 fields, 6 different pointings that have been merged together. There are 5 different filters in each of those, so that's up to 30 now. And there's 3 exposures of each filter, so that's going up to close to 100 separate exposures that have gone into putting this picture together. And even though it's a beautiful picture as it is, as the really amazing part about this is as you zoom in, you see the Hubble resolution all the way in as you go to smaller and smaller fields of view and see the tremendous detail across this entire image. It's really spectacular.
How does this galaxy compare to the Milky Way?
It has much stronger spiral arm definition, if you will. It's got 2 big, strong arms in the spiral. You can see some little flares that come off the main arms, but it's basically got 2 main arms and a very, very bright nuclear region. Our Milky Way galaxy, I actually saw some things just at the American Astronomical Society meeting that were talking about the Milky Way possibly having 4 spiral arms. Really, it was, from what I could tell, was 2 main arms and 2 sub-arms that came off in between the other 2. So that might be a difference. But I think the biggest difference really is in terms of the size of M83 and the rate of the formation of new stars. Basically, this galaxy is forming stars approximately 30 times the rate of the Milky Way.
Nice.
A lot faster, a lot more star formation. But size-wise, if we could plunk the 2 down next to each other, in linear diameter, M83 is about half the size of our Milky Way. So the area, if you would be sort of like a quadrant, a fourth of our Milky Way galaxy. So as impressive as this looks, relative to the Milky Way, it's a relatively small galaxy.
Okay, while we're on this topic, Ken Howard is asked on the event page, what is the shortest lifespan for a star?
Really, about the shortest one would last is about 3 million years. The most massive stars take about that long to finish burning their hydrogen to helium in the core, and then the subsequent evolution goes very quickly to the explosion of the supernova.
Good. So these are usually massive stars that are short-lived, right? They usually are the shortest-lived ones, the ones that burn the brightest.
That's correct.
Good. Thanks, Kevin. Okay, so this galaxy is smaller than ours. It's presumably younger then, if it's got a higher rate of star formation, maybe?
Well, the age of the galaxy is a little bit different than the age of the current star formation. So it clearly has a lot of young stars being formed currently in this galaxy. One of the reasons that we are very interested in it, as a matter of fact, M83 is in second place right now. It has had 6 actual supernova explosions observed since 1923.
Wow.
The leading galaxy looks very similar to this and has had 9. So we're in second place here looking at this galaxy. But we know there's been a lot of supernova activity over time in this galaxy.
Here, Bill, why don't you give the name of the first one? Because people probably want to go off and Google it now that you've mentioned we're number 2.
All right. Number 1 is it has a new general catalog number, NGC 6946.
That has the highest rate of star formation.
And that's the highest supernova, observed supernova rate.
Oh, okay.
Yeah.
All right, so you've explained what the dark stuff is. You said that's clouds from dying or heavier elements in clouds from the deaths of stars. What are all these bright spots? What is all that? See all the bright pink things.
Yeah, so when you look around, you see the most of this the pink fluffy stuff, as well as the dust in a lot of ways, is concentrated in the spiral arms of the galaxy. That's where most of the star formation is going on. And these giant red regions that you see and you can zoom into with the zoomable image are indeed some of the things that you will be measuring. There are clusters, stars that have formed in the center of these regions. The youngest stars are the hottest stars, and those are the ones that can actually ionize the gas around the region, and that's what you see is the pink fluffy stuff. That's ionized hydrogen being excited and glowing because of the very hot stars that have just formed. And so as those stars evolve away and become supernovae, the light turns out. Basically, the pink goes off and you leave a cluster behind that doesn't have the red or pinkish gas around the cluster anymore. That's one of our age diagnostics.
Good. So these, the star cluster citizen science identification or classification program. Star clusters are important because generally the stars in a cluster have all formed from the same stuff, more or less. They're all kind of more or less very similar to one another. Generally have the same age. But the clusters themselves will differ from each other because they were born at different times and at different spots in the galaxy. So I'll ask you in a minute what you're hoping to learn from this as far as the statistics go, but before we get too far down, I want to have Scott give it a try. Okay, Scott, you are on. So go ahead and share your screen and let's see what...
Let me get back up. I was tweeting.
You were... Oh, yeah, that's another one of the things Scott does.
In the interim, while Scott's getting ready, I just wanted to mention that in addition to understanding about the star clusters themselves, the distribution of the clusters, how fast they form, tell you about the galaxy itself.
Right.
So one of the questions who study star clusters, we pose to ourselves is, does the star cluster know what galaxy it's in? And that's a cute question, but what it means is there something about the environment of a particular galaxy which is producing lots of star clusters, and then as Brad said in our own, and Bill was also talking about, in our own galaxy that rate is not so high. Why is that? Does it have something to do with how much dust is in it, what the chemistry is it interactions between galaxies? So star clusters don't only tell us about themselves, but they tell us about the parent galaxy as well.
Good point. Excellent. Okay, so Adam Synergy is asking a really relevant question right now. Are we looking at M83 exactly face on, or is it at a slight angle? And are the lower spiral arms slightly closer to us? Who wants to take that?
It is at a slight angle, but only about 24 degrees away from being exactly face on. The sense of things is that actually the top spiral arm is a little closer to us, and the bottom, it doesn't really look that way to look at it, but the bottom spiral arm is actually a little farther away, so it's tipped.
Yeah, I can imagine that kind of tilt would be difficult to make out.
So a related point there is that it's actually slightly barred, which is why the shape is a little bit misleading. It's not fully barred; it's kind of a mixed thing. But if you next time you have a nice picture up, take a look at it. You can kind of see where the slight bar is.
Oh, okay. And Brad, you're still screen sharing, just in case you weren't aware of it.
Okay. I should get rid of that. Sorry.
Yeah. Okay. So there you go, Adam. Good question. That was very relevant for what we were doing. Okay. So Scott's got it up now, and you are looking at the classification interface, the simpler one, right? There's two kinds, right?
I am a simple man. All right, Tony. Don't judge.
Yeah, I know that. Okay. So this is what. So Scott's looking at a cluster now.
And this is my first time doing it, so I hope I'm doing okay with getting this ellipse on here. I think this is what we're looking for here. I'm not sure if the diameter...
Adjust the ellipse to include only the cluster in the center of the image.
So you already classified it.
Yeah, you already said it was ancient.
I'm saying it's ancient.
Okay, we didn't see that step, but okay. I just wanted to point that out. You were doing that.
We're picking him up in the middle, I guess.
Yeah, he's already started. Okay, go.
That's why I do.
Okay.
All right, next cluster. Here we go. Let's start from the beginning. So, am I seeing a cloud around this or no cloud? I am not seeing a cloud around that. So
Good answer.
No cloud. So, can I see the individual stars within the cluster, or is it fuzzy? I'm going to say it's fuzzy. I'm not really seeing much resolution going on in there. I'm going to say it's whitish blue. And you're right. It's really hard. I'm going to say blue. I am seeing a little bluish hue there, and I would say it's more blue than white.
Why don't you go ahead and zoom it up a little bit? That might help you see it a little better too.
Well, that is zoomed in.
Oh, it is. It already is. Okay, that's a kind of a small one. Good.
So I'm going to say bluish.
Okay.
Carol's like, okay.
Excellent.
Carol's going to judge you now.
Yeah.
Judge me all you want, Carol.
Yeah, I can do these very fast.
That's fine. And so, yes, I'm going to zoom in here and do this a little bit more. And I'm using a trackball. I'm not on my computer, so this is really hard to get it precise.
Okay.
There we go. And done. And anything else that I should mark?
So what's the ellipse for again? What's the point of drawing that? Just to kind of get a size for it?
Right. Just some clusters are very concentrated and some are more diffuse. Now we can measure that pretty well, but in some cases, if it's a very crowded field, it's pretty hard for a computer to kind of say, am I still within the cluster or am I in the background stars? And so it's kind of to double check that our size measurement is right.
Okay.
And the other thing is that the size of the pink clouds is very, very important. And so that's the other part. We don't happen to have a pink cloud in this case, but...
Right.
Could I just make a comment about the size before Scott identifies more? You know, we say, oh, the computer can do it. Where do you think the computer got the algorithm? They got the algorithm by people looking at clusters and writing an algorithm. And that means that the algorithm is not perfect. And so we have to keep improving the algorithms by having lots of people with different perspectives look at the clusters and compare to the algorithms and say, maybe we can actually improve our computer algorithm. So just because there's a computer algorithm doesn't mean we're done. Computer algorithms always, they came from people who visually looked at imagery, and they will be improved through the same process.
Well, and correct me if I'm wrong here, but humans are really good at recognizing patterns and things, and so we're able to really draw these connections from different examples we've seen before.
Absolutely.
Okay, so one more, and then I want to move on to the next. What's that cloud thingy up there?
I put a black cloud there because it looks like a black cloud up here.
Oh, okay. How'd you do that?
I clicked. So I clicked here. So I clicked.
Good work, Scott.
I know. Man, it's like I've done a lot of physics in my time. So I just clicked dust cloud and it put it right there.
Got it. Okay.
Now
I think we should change that to read dust bunnies there, but anyway.
We should do dust bunnies. I like that.
Yeah, right.
All right.
So
awesome.
I'm sure there might be more things to classify.
I think I see a red blob.
I do. I see the red blob. I see the red blob.
All right, red blob. So technical.
Yeah, really. Yeah, you really needed it. Dust bunnies would have been funny.
I like dust bunnies.
Okay, so red blob.
Anything else? All right, I'm going to go with one more. Let's do this.
We probably should just emphasize that this is kind of for fun. I mean, we're going to use the information that you provide by those ancillary markings that you're doing there, but of course it is separate from the age dating of the cluster part of the project as well. So it's optional, but we hope you have some fun with that.
Okay.
No, absolutely.
Yeah.
So let's see, pinkish cloud roughly centered around the image. There's so much density in here. It's hard to tell.
You got a busy one.
I know.
There's a lot of pink in the image.
There's tons of it. So experts over here, what would you?
Why don't you zoom out again?
No.
No, you don't. No prompting from us.
Let's make a fool out of Scott on here. This is great.
No, you have to do it, and then Carol has to judge you. So.
I love this game. This is I'm going to say there's a bit of a cloud. I'm going to say there's a cloud around it.
This is very interesting, actually, because this is part of what citizen science does. Different people are going to do different things with this particular situation, right?
Right.
And so when we look at the ensemble of measurements that people have done, it automatically tells us that this one must be in a confused region or something because people are getting widely different answers for it. So you just do your best shot. You take the questions and you do your best shot, and whatever you
don't want to let Carol down.
You're trying.
It's impossible to let us down.
Okay. I might just go and cry when we get off air. With it, it's fuzzy, and that's hard to tell. It's pink. It's all pink. There's blue here. I'm going to say white.
So the cluster itself is what's centered, right? That's okay.
Right. Yeah, we got the crosshairs there. You can blink the crosshairs on and off if you want to be a little clearer.
So you found all these clusters. Well, I'm gonna let Scott finish. I'm gonna ask you how you.
Yeah, let me finish, Tony. No pressure, okay?
Yeah, really.
Thanks.
Hurry it up, dude.
All right. So I'm gonna say it's there. Done.
Why don't you go to the Where Am I? This will be a fun one to see. Where is this cluster in the galaxy?
Anyone want to guess? Am I near the galactic, the center, the bulge? On one of the arms?
Or you're in an arm.
I'm on one of the arms. There we go.
Yeah. Cool.
Oh, there we go. Yep. See, you learned something right there. The young star formation is in the arms.
Look at that resolution, too. I mean, look at the...
I love that.
Yeah, look how tiny that circle is on the galaxy. And it's really... Hubble's a pretty darn good scope. Okay.
All right, let's see. Drag and draw an ellipse around that. I did that. Done.
Okay.
And anything else? I see in some dust bunnies.
Oh, you see a lot of stuff in this one.
Yeah.
We're going to be here for another 40 minutes. I'm going to get these all classified.
All right, so you can kind of do this until you get tired, huh?
Yeah, you don't really have to mark everything in every frame. It's really optional. So.
Okay. All right.
Very good.
While he's got it there, if I can ask, hit the done. Oh, he's doing a bunch. Hit the done and then go to discuss, just so we show people the discuss page, and you can have little discussions like what we've been having right now.
Okay.
Well, I would need to sign up on this here.
Oh, yeah.
You have to have an account. That's where.
We're gonna put Laura to work in a minute here, and she'll explain what you need to do.
Yeah.
Yeah, Laura, tell me what I need to do. It's been so long. I think I have a Zooniverse account somewhere.
Yeah. Okay.
I don't want to screen share that though.
Yeah. Let's get Laura into this a little bit. It's a good segue into that. So Laura, obviously Zooniverse has a lot of citizen science projects that it has sponsored up there. How does this one fit in terms of scale and scope to some of the others that you've done?
So, well, it's part of a growing collection of astronomy projects. We seem to have great success with astronomy projects.
Oh, I know. You guys have all kinds of great stuff.
Yeah, so this one's a little different in the sense that generally speaking, we build projects for people, but this time this has actually been a collaboration where the team at Space Telescope have used our technology to build their own website. So that's that's kind of moving in a slightly different direction for us, partly because we've recently received a Global Impact Award to kind of generalize some of our technology. Eventually, we hope to get to the point where building a citizen science project will be a bit like spinning up a blog. It should be that easy. So I hate to say it, but you guys have been the guinea pigs in that direction, and we've learned a lot from this experience.
Well, that I did not know. So STSCI is the first place to take your, let's call it an engine, and put it on our own servers and run it.
Well, no, you're actually on our servers. So, except they're not our servers; they're Amazon Web Servers.
Well, okay, the Amazon servers.
So they're all up in the cloud there, and but it's using our technology. It's using the tool sets that we've built.
Okay.
So that's been a lot of fun. This project is slightly different because the number of objects in the collection are it's about 3,000 objects, and we've had a lot of jokes about. I keep going, oh, it's such a small data set, because a lot of our projects have millions of images rather than thousands.
Well, that's where I was going with this. I was wondering how it compared in terms of number of objects.
Yeah, no, it's smaller from that sense. So I would imagine it's going to get done really quickly, which will be hugely exciting because it means you're going to have results and real science coming out of this in a matter of...
Only 3,000 globular clusters in this galaxy? Bill?
Only?
Well, that's a pretty big galaxy. It seems like, I don't know, it just seems kind of small to me anyway. Okay, so...
there are actually more than that, but some of them are in confused enough regions and whatnot that Brad decided to pull the plug on them. So we've got a few more than that, but we have about 3,000 to measure, so...
Okay, but Laura, so the sample size may be small, but statistics will be good, right? I mean, ideally, you want a lot of different observations and classifications of the same thing. So
the statistics have the potential to be better than if a group of astronomers were to classify themselves. Chris Lintott, who founded Galaxy Zoo in collaboration with some other people, wrote a paper a few years back about how the combined effort of citizen scientists can be just as good, if not better, in some cases, because you have so many classifications of each object. Mm-hmm. So you not only get kind of a classification for that object, but you get kind of a probability distribution. So as I can't remember who was saying earlier, but the uncertainty in the classification tells you something interesting. If it's difficult to classify, if there's a lot of disagreement, that's a piece of useful information because that tells you it was a confused, tricky object. Whereas if 100% of people say it was that, then you know that you have utmost confidence in that particular classification.
Another trick that you can kind of do is if you've got 100, you can find, say, the 30 people that seem to really know what they're doing and have the best correlation with the ages, and you could just go with those too. So with the statistics, you can play all kinds of games.
Yeah.
Okay, so Harrison Wynn has asked how many clusters have been classified by this project, which is directly what we're talking about. So I put that up there. And Bill, you guys have said like Laura said like 3,000. So were those found using automated techniques, or what was? How do you know there's 3,000 in there?
Yeah, it's a combination. Now another project, and she might mention, is the Andromeda project, and in that project it's a closer galaxy. The Andromeda galaxy is about 7 times closer than M83. So in that case, they had them find the clusters. In this one, some of them are kind of small and it's a little harder. So we found the clusters for them, and then we have them help us with the age dating. So we use a combination of algorithms to try to find them, but then we manually look at them and throw out the ones that are kind of in crowded fields and probably are just pairs of stars, etc. So we did find them for them, and it's a combination of an automatic and a manual technique.
Great. Okay, so about 3,000. Thank you for that question. That was really good. So Tom, I want to get you in here on this a little bit. You were the one, I think, were instrumental in getting the Zooniverse connected, or getting our stuff connected to the Zooniverse, correct?
Well, the Zooniverse developers were more instrumental than I was. But yeah, I worked with Brad and our team here. We had Stephanie Smith, the graphics designer, and helping out to come up with a user interface that would hopefully answer the questions that Brad and Bill were asking. And there were a number of iterations with that. It was kind of interesting. You see, Scott certainly saw a few steps along the way that it can be a little confusing because we're not just asking one question. I think that's an interesting aspect to this project as well. We're not just saying, what shaped galaxy is this? And then you see the next galaxy, what shaped galaxy is this? We're asking a series of questions, and those questions help to get you to what age the thing is, the cluster is. And then, but then we ask you to measure it, and if there's a cloud, we ask you to measure that, and then can you look for some other things? And it'll be interesting to see how that works out, but it was sort of challenging to put that in a coherent interface, and hopefully people will find it coherent enough. But then on the Zooniverse side, they've come up with a very nice infrastructure for being able to collect this data, and a lot of the peripheral things around it are quite nice. The talk feature where you can discuss different subjects, all that. Seems to be very generic, so it really can apply to all their projects, and so it really was just a matter of plugging into that infrastructure to be able to get the data gathering, to be able to share the user logins with other projects, and share the talk feature.
Well, that's a good point. So you were, like, as Laura said, you were a guinea pig, or we were guinea pigs in setting this up. Well, how would you, and as a computer scientist, as someone who does a lot of developing, how would you rate that experience? Would you say that it's, they've lowered the entry point so that it's pretty simple to start one of these up on your own? How would you characterize the experience, I guess?
Yeah, well,
from a technical perspective of connecting to them.
Yeah, from a technical perspective, it's clearly a successful thing in the sense that I would recommend that other projects could do this, and I'm sure, in a couple weeks when all the dust sort of settles on this, that we'll go through and sort of figure out the lessons learned, and maybe work with the Zooniverse side to find out the parts that were hard for us, and maybe areas where we could have communicated a little better, but overall, I'd say, from a technical perspective, they have a very strong interface, and really that trumps everything when you want to connect to something.
Yeah, a good API or whatever to get connected. So Laura, it sounds like as guinea pigs, they were pretty happy with the experience. So you guys did some great work.
I think as Tom says, though, there's going to be a lot of lessons that we can learn from this process, and hopefully it means that in the future that we can create a much more streamlined system that really helps scientists kind of bring their data, put it online, ask questions of the public that they need help with, and do this in a much kind of slicker, smoother way. But thank you for being the first.
Yeah, good. Well, hopefully this is the first in a great many other people doing the same kind of thing, other observatories, other projects, things like that. I mean, what immediately comes to mind is finding out something to do with Kepler's field of view that might plug in nicely, but I don't know if that's even possible, or even what questions to ask that data set. But that might be.
I think we should actually ask Laura to talk a little bit more about some of the other projects, because one of them is Kepler related.
Oh, okay. Go ahead.
Do you know how to screen share, or should I bring up my screen? I've got Zooniverse up, and you could just talk to it.
Okay, go ahead. Go ahead, Brad. Bring it up.
Okay.
Quickly, because I want to get to a couple of questions. We're running out of time. So.
Right. Okay. There we go. Here we go.
So I think Brad's about to bring up Planet Hunters, which was a project. I think it's nearly 3 years old now. It actually uses data from Kepler. It's light curves, and we weren't sure whether this project would be popular, but it turned out to be wildly successful. And I think that's because everyone wants to find their own exoplanet. I mean, who doesn't want to, find an exoplanet? But we asked people to look for transit features in the data set, and there's been at least, I believe we're up to 4 confirmed planets that were discovered using this website, which is...
Now let me just show the things at the bottom here, because people may not even know these exist, and maybe just 30 seconds on those.
Yeah, and anyway, so a couple of years ago we had a grant from the Sloan Foundation to see if we could take this technique that worked so well in astronomy and apply it to other fields of research. So we now have climate science projects, we have biology projects, we even have a health project where we ask people to identify cancer cells. So it's citizen science, this kind of technique of taking large data sets, putting them online, and asking people to answer questions about them works across a whole range of disciplines, which is one of the reasons we're so excited about kind of generalizing our platform so that anybody anywhere can build a citizen science project.
Yeah, you guys are really branching out. Brad, what URL are you on?
Oh, okay. Well, Zooniverse.org, I assume, or what's...
Zooniverse.org, and
Okay.
I've just had word from the team that they are in the process of rebooting Zooniverse.org. So any minute now, you should see the project star date should be on there. They are actually doing it as we speak.
So stand by, the universe is rebooting.
Yes.
Okay. All right. Well, I want to get to some questions. We're running out of time. There's a really good one here from Andy Cowley on the Q&A thing, asking how many black holes do we think are in there? Presumably, I'm meaning M83. Any idea? Is there a supermassive black hole at the center, or are there a bunch of little bitty ones running around?
I would say more than 0 and less than infinity.
I'm showing. Did I share a picture of red and orange version of M83? Do you see that?
We don't see it yet. There it is.
Yep.
There, now we see it.
Folks, this is an X-ray picture of the same galaxy we've been looking at, M83, taken with the Chandra Observatory. You see the very bright nucleus where the star formation is going on. You see some indication of the spiral arms with diffuse red. In this case, that's low energy X-rays. The green and blue is higher energy X-rays. Many of those little blotches of light you see there, the greenish and whitish and bluish objects, are black holes. That is to say, strong X-ray sources. Some of them have optical counterparts, most of them do not. And this object over here in particular is about a 40 solar mass black hole that we found when we just started taking these data. It was not there in 2000, and in 2010 that source had shown up. There's also a supermassive black hole in the center, and there may actually be a couple of them kind of dancing around each other in the center of this galaxy from a previous merger of a small galaxy with this larger galaxy. So lots of, probably dozens of black holes in this galaxy.
That is so cool. So those bright spots are the jets from the black holes, right?
The bright spots are really just the X-ray emission coming from an accreting black hole. So you're seeing matter pulling into the black hole, and the X-rays are emitted as part of that process. That's how they show up.
That is so great. That is really cool. Good question, Andy. Thank you. Okay, on the event page, there is a question I wanted to grab. I hope I didn't run down. Oh, Michael Kaminsky is asking, hey, any chance I could run the page on iOS? Laura, can you talk about that a little bit, about some of the different OSs that this can maybe be run on? Can't get through the tutorial measurement stage, it says.
Yeah, I'll field that a little bit. Early on in the project, we had some discussions about whether to make the activity mobile friendly, and perhaps regrettably we decided not to put in a little bit of extra effort to do that. Certainly, that would be something we would do in the future, because an activity like this really would probably work very well on an iPad or various other tablets. But no, we didn't enable that for this particular.
But it is an option, though, Laura, to have mobile friendly.
Yes, yeah, certainly. We are moving towards trying to make sure that the majority of our websites work on an iPad at very least. Generally not a mobile phone, because that doesn't lead to a very good user experience, but usually a tablet. But as Tom says, it does take just that little bit of an extra push to make that possible.
Oh, okay. So that's exciting. That's a big step forward, actually. I would imagine that's not less than challenging, or extremely challenging to do. So Kevin Howard is asking, has Kepler found a planet anything at all like Earth? Its basic size and distance from the star? And I can answer that because I was just at AAS. In fact, on Monday they announced that they did find. Actually, Kepler has found plenty of Earth-sized planets, rocky planets. Carol, I know you got something to say on this. You got a comment on that? Any idea?
There's quite a range.
Carol,
you're muted, Carol. I didn't realize we could do that to Carol.
Yeah.
No, that's very funny, Scott. That's very amusing. You were muting my dogs who were asking for dinner, actually. There's quite a range of planets that have been discovered. So in general, I would say the combination of a planet, a star just like the sun, and a planet just like the Earth has not been found, but they're pushing down to Earth size. More common, well, the most common are very giant planets like Jupiter and Saturn, but there are a class of planets that they found that are called super Earths, and there are a couple times the size of the Earth, and some of them are in the right place where they might have water, and some of them are not. So that's a lot of follow-up work to make sure exactly what the temperatures are on those planets to see if maybe there is water, and then who knows what else.
Yeah, Kepler's only just started in terms of what it's going to have discovered. While it may not be taking data right now, they're still sifting through the years of data they've taken so far. So we've only just touched the surface of the kinds of things that Kepler.
And there's a lot of follow-up work that scientists need to do to verify all of the exact characteristics of the planets that they found.
That's an excellent point. Yeah, that's right. Because once Kepler finds candidates, then it has to be confirmed in some other way. So that work is ongoing, and we're going to be hearing about this in the coming years. So lots of work from Kepler, and as Laura's pointed out, Zooniverse has got some things planned with them as well. So I guess we're out of. Well, we've got a few more minutes. Let me see.
Can I take 2 minutes there, Tony?
You want it? You can have it.
Okay, thank you. Let me screen share again. Okay, I want to show a couple more things for people that might actually be using it, etc. And so one was the discuss page, which again Zooniverse has a beautiful infrastructure for. And for example, as recent, here we are at recent, and people put up their images and talk about them a little bit. There's a discussion board, and the main reason for pointing this out is that we've got the FAQ in here. So go ahead and take a look at the FAQ to get a little bit of help in some cases. Even the iOS question was in here already somewhere, right there. And the final thing, and I want to, let's see here, return to classifying. I want to make sure that people don't underestimate the role that Tom Donaldson played here, and give him a personal thank you, because he's put tremendous amount of work and expertise into this.
I had a feeling that he was being pretty modest there.
Here is one of his nicest little touches. Here, it's my data. There you are. This is all the clusters that I myself have gone.
I love that.
Yeah, and you can go ahead and make them favorites. Get a little blow up here. You can see that this is kind of where he built his "Where Am I" feature from. So thank you, Tom, and I'll kind of close with that.
Oh, awesome! It's excellent. Excellent addition. Thanks for doing that, Brad. I appreciate it. Okay, guys, well, we are out of time. So it's projectstardate.org. It is one of the latest areas in which the Zooniverse team has gotten Hubble involved in citizen science, and it looks like a really good way to get involved and to help these guys understand M83 a little bit better and the life cycles of these galaxy clusters and stars. So please, I encourage you to log in and have fun and interact and discuss and do. And I want to thank all of you guys for joining me. Bill, Brad, Carol, Laura, Scott, and Tom. Thank you all very much for joining and helping us understand what you guys are doing. Look forward to seeing what comes out of all of this. So Laura was alluding that maybe this would be over relatively quickly. Do you have a time scale? Do you think? Because I'm thinking maybe we should follow up, find out what you found out.
Yeah, I mean, it's impossible to say exactly how long it's going to take, but I would think that 3,000 objects shouldn't take a huge amount of time for the Zooniverse community to go through.
So we should plan on doing maybe reconvening at some point after it concludes in the near future and seeing what was learned. Okay, what do you think of that idea?
Sounds great.
I just wanted to thank, in addition to Laura and everybody at Adler, public thank you to Chris Lintop for that afternoon in the pub over many beers where we dreamt up this collaboration that we were going to do part of it. Sorry about that, Tom, but that's kind of where it originated.
And I've got one more thank you for Stephanie, who is sick today.
Stephanie Smith.
She played a tremendous role in the graphics, which you can see here.
She does awesome work. I'm always impressed by the work she does. She's done some things for me too. It's just been great. So yeah, that's awesome. Okay. All right, Scott, thank you. Did you learn a thing or two about the science today?
Honestly, I've done many different citizen science projects, and I really like that I have more options than that just yes or no or just what's a general shape. I like getting a little bit deeper in, so I can see it being something that I really want to get into, and it'll be a huge time suck because I don't have enough going on in my life. I need to just dig into something new.
That was the problem I had with the original Galaxy Zoo, is I was just clicking on these galaxies. Next thing I knew, an hour had gone by, and I'm like, oh man, this is like, I got to do something
videos
else.
to do, and things are right.
Okay, well, that's it for this time, Hubble Huggers. Yes, I called you that. Thank you all for watching, and as always, keep looking up. And with me also is Dr. Bill Blair. He's an astronomer at the Johns Hopkins University and at the Institute. Hi, Bill. You're going to be here to help explain us some of the science behind what people are trying to do. And,
yeah, looking forward to it.
What's that?
Looking forward to it.
Yeah, great. Thank you and welcome. Also is Dr. Carol Christian. She is the HST outreach scientist and a geek goddess. You want to explain that?
For one brief minute, yes, we had a press release. For 1 week, I'm a geek goddess with my collaborators. We are creating a completely different project. We're creating 3D printouts of Hubble images, and in particular, putting textures on them for the blind, and we'll do a hangout on that sometime in the future.
Yes,
we will.
Great.
I will make you, Carol.
Okay.
I love it. They're amazing.
We'd love to.
And also is Laura White. She's from the Zooniverse team. Is it Doctor or just Laura?
It is actually, yeah, it's Doctor.
Okay, good. Dr. Laura White. Welcome. She's going to describe to us a little bit about the collaboration with M83, the M83 project, and also if you've never heard of Zooniverse before, which I would find it very amazing if you did not, then she'll also get us familiar with that as well. So welcome, Laura. Thank you.
No problem.
And finally, we have Tom Donaldson. He's the what are you at the Institute? You're like you're an astronomer too, right? You were in the data archive and MAST and things like that, right?
No, I'm a computer scientist.
Oh, okay.
Mostly currently working for the MAST archive.
Okay, so you were instrumental in getting some of the behind.
I actually wrote a paper here in 2011 where we gave that a try. So I won't describe how astronomers generally measure ages in detail, but they use the colors. And the thing is here, I thought by just looking at them, I could also estimate the ages. So I put together this little paper, and these are essentially what the citizen scientists are going to do. You can see for the very young ones, they have this pink cloud around them. That's from hydrogen gas. And as soon as you see that, you know it's very young. And then if you can see the individual stars here, that's young or intermediate. And then they get kind of fuzzy looking. And then most ancient ones have this kind of yellowish picture around them. Now, a question I get asked a lot here, why are we doing this with citizen science? Why don't I just have the computer do the whole thing? And the bottom line for this project especially is it's that H alpha. It's the hydrogen emission, the pink clouds. As you can see, they can come in any shape and size. And so if I just plop down an aperture and measure the colors, in many cases I've completely missed the hydrogen. And so it's much easier for a human to look at that and say, oh yeah, okay, well it's kind of centered around it. I think it's blowing this bubble of hydrogen. This must be a young cluster. So
let's go back to that just real quick, Brad. That aperture, that yellow circle there, that is what would be used by an automated program, right?
Exactly.
If you tried to do this automatically without a person, an automated program would easily miss any hydrogen because of where. Hello, everybody, and welcome to our latest Hubble Hangout. My name is Tony Darnell. I'm the social media manager for the Space Telescope Science Institute, and we haven't done one of these in a while. This is our first Hubble Hangout, I think, since November. Is that right, Scott? Something like that?
I think it's been November. It's been a while. You and I have been in trouble.
Yeah, we've been doing other things, but I think it's our first one since then. We kind of took December off a little bit. But this one is the first one of 2014, and it's a really exciting one for me because it's all about citizen science. So today we're going to be showing you a brand new initiative that has been launched today that allows you to help astronomers do science using the Zooniverse, another project in the Zooniverse universe, I guess. The Zooniverse universe. So with me today is a whole host of people that were involved in the project, but my co-host, as always, is with me, Scott Lewis from KnowTheCosmos.com, also known as the Bald Astronomer. Hi, Scott.
How's it going, Tony?
You're going to be a guinea pig today.
No, I feel like guinea medium.
Guinea.
Hey.
Because we're going to have you step through.
I have not gone through this software, so I'm going to test out and see how this citizen science project works, and I think it's really cool being able to find the age of stars in this galaxy.
Yeah, it's going to be. Well, that's one of the great things about all of the Zooniverse things is how it gets people involved, and Laura, I'm sure, is going to help us talk a little bit more about that as well. But before I get going and introducing people, I want to let you guys know how you can interact with us. Always use the Hubble Hangout hashtag if you want to. The Hubble Hangout hashtag if you want to tweet.
The alliteration is strong in this one.
I know. I just can't help myself. I always have to do that. And so that's how you can get our attention on Twitter. I've got that up on my tweet deck. We're also taking comments via the Q&A app on the event on Google+. If you ask a question on that, you push the button and ask a question. We'll see it, and we'll try to get to it as soon as we possibly can. There's also the YouTube comments. I'm looking at those as well. And
be nice, YouTube.
Yes. Yeah, well, actually, they kind of have to be nicer now because YouTube is making them. They're making them more accountable for their comments now, which is kind of nice. So that's how you can get a hold of us. We will have a segment toward the end, or maybe even throughout, if it's something that's relevant to what we're talking about. I'll interrupt and ask your question during the Hangout as well. So let's get started. And let me start by introducing Dr. Brad Whitmore. He's an astronomer at the Space Telescope Science Institute. And I think you are the PI for this. Is that correct, or am I?
Yeah, pretty much.
Okay. So why don't you describe for us what this is we're doing today?
Okay. Let's see. So I should grab and share. Screen.
Hang on just a second before I do that. I apologize. I want to get through. I want to introduce everybody first. Behind the scenes stuff written and getting the nuts and bolts going, right?
Yeah, I worked a lot on the user interface and figuring out how to talk to the Zooniverse world, which was a lot of fun to learn about.
Oh, good. That's great. We're going to find out what you went through to do that. So let me get back to, and I've already introduced Scott. He's got to just cause mayhem whenever possible. So, Brad,
I'm breathing, right?
Give us an overview of the project, what it is you're doing here.
Okay. Let me jump to screen share, grab this one here, hit the little button, and I'm live, right?
You are live.
Yeah.
Get your PowerPoint.
All right. So I'm stealing a couple view graphs I used at the American Astronomical Society meeting last week. And so the name of our project is Stardate M83. It's a citizen science project where the goal is to age date star clusters. And the centerpiece is this wonderful new Hubble Heritage image right here. Maybe you've already seen that. If not, you should Google that and go find a zoomable image. It's really fantastic. This is the first time that we've actually had a Hubble Heritage image with a citizen science program attached to it. It's a joint project with Zooniverse and the Institute. And before I forget, this has been a real experience and a tremendous team to work with. So I want to kind of thank everyone involved, people online especially. Okay, so what is the science behind it? In a nutshell, the idea is that we think we can measure the ages of star clusters by simply looking at them.